Hello, my name is Ernest James. This past summer, I've had the wonderful experience and honor of working with Dr. Chen on the use of mathematical modeling on COVID-19. This project was made possible with funding from the CITO Summer Undergraduate Research Experience. Now, COVID-19 has completely changed everything but how we learn, work, even eat. But I'll focus for this project primarily on the states of North Carolina, South Carolina, Tennessee, Georgia, and Florida from the 4th of March to July 20th of 2020. This was when the virus itself was just coming about. This was when the virus had just come to America, where we were just beginning to implement lockdowns, social distancing measures, and just beginning at the very end to start using masks even. And this is when schools had begun to shut down, spring breaks were cancelled. This is at the very beginning of the coronavirus epidemic. Now, our goal is to determine the effectiveness of social distancing measures and lockdown orders. We want to know, did this work? Did these lockdowns slow the spread of the virus? And we also want to predict the behavior of the coronavirus in the 5 states. We want to know what happened, did it work, and what's going to happen next. Now, in order to do this, we want to first develop the periodic, linear, quadratic, and exponential models using a regression method with the data reported by the COVID Tracking Project, and use the developed models to analyze the effectiveness of social distancing measures and lockdown orders. Then we're going to develop a dynamic mathematical model to predict the future growth of the coronavirus in the 5 states. Now, first we have the periodic models. Now, the periodic models, the goal is to have the data. This time it's already passed. We have the data, and now we're analyzing it. First, we divided the time period into 3 separate sections. The first period was before the lockdown social distancing was implemented. This was at the very start of the epidemic. No lockdowns, no social distancing. This was from patient 0 in each of these states until the lockdown was issued. This is the baseline. Next step was what happened during the lockdown. Was the growth slowed? And then the third step was after the lockdown, when the lockdowns began to lift. And also, we marked this time period as a time when George Floyd died, because at the same time of his death, these 5 states had begun to lift through though at separate times, all around the same time, and more importantly, across all 5 states, there were massive protests. Protests with no social distancing, and that did unfortunately act as spreading events for the coronavirus. So we used this specific date, the start of these protests, and the relaxation of the lockdown orders, as the stage 3 period, as in after, post-lockdown. Now, the goal is to learn how was it effective. So for each of the 3 periods of each of the 5 states, we developed a linear or quadratic and exponential model. Now, in order to determine which is more accurate, we use the R-squared value. The R-squared value says, ideally, you have a 1, an R-squared value of 1. This means that for every single data point, the line of best fit matches. But the greater the discrepancies between the line of best fit and the data points, the lower the score. So we took the best score for each of the 3 periods in each of the 5 states. And we're also able to, as you see here at the bottom, this is where we began to judge the efficiency, the efficacy of the lockdown. And we'll get to that more in a second. This is where we're able to determine what happens in the future. Because unfortunately, the periodic models, what's normally linear growth during the lockdown, well, that's based off of data when everybody's staying socially distant, separate from each other. But as soon as these protests happened, as soon as everybody got together, as soon as the lockdown was lifted, the previous data isn't really as relevant to the new data. So we need to be able to make a dynamic model. Now, to do this, we create an algorithm in MATLAB. The algorithm follows a few steps. First step is to create 3 types of models using a regression method with 10 consecutive data points. Then it calculates the R-squared value for each of these regressions. Now, using the R-squared value, it chooses a specific model to go with. Now, choose the linear model if the exponential and quadratic models are not very accurate. But if the quadratic model is accurate, then it will choose that one. And if the exponential model is more accurate than the quadratic or linear, within a margin of error, it chooses exponential. As you can see, the exact error is listed down here. Now, this chosen model is then tested with data from the days after this period. And after this point, it checks the next day and it sees, does have an absolute error of 6. Is the guessed amount of infections different from the actual amount by more than 6 people per 100,000? And does it have an error of more than 10%? As in, is there greater than or less than 10% difference of the error? Does it go over by 10% or under by 10%? If it does both of those, then it will create a new model using that day and 9 days back. But if it doesn't meet those two conditions, it's considered an accurate guess, and it keeps moving on to the next day. Now, here in these tables and graphs, in the top right, you can see the period and models table for each of the periods, each of the 5 states. What this table shows is for the first period and the second and third period, it shows for each of the states what type of model was considered the most accurate. For example, the first period, exponential models so far to the 5 states were chosen. This means we saw commonly exponential growth. For the second model, we saw constant growth because all 5 states, their most accurate graph was linear. And then for the third one, it didn't get as bad as exponential growth, but we still saw quadratic growth, which, as you can see in the bottom right of your screen, looks a lot like Florida's graph did. It's not as steep as an exponential curve would be, but it is more significant than a linear line. It has more growth than constant. We're seeing more cases each day than the last, but not at such a rate that would be considered exponential. Then in the middle, we have how we can judge efficacy. First, we look at the number of cases per 100,000 that existed. This is what actually happened in the top. For example, South Carolina had roughly 1,400 cases per 100,000 population. And then we took all of those linear models from the second period and we extended them to the 20th of July. From the day that George Floyd died, 20th of July, we extended it. And we saw in South Carolina would have been, if the lockdown had happened and no protests occurred, 366 cases per 100,000. So that means that there should have only been 26%, if lockdown had happened, cases as there were. In North Carolina, it would have been 71%. But that all 5 states, we said if the lockdown had occurred, the amount of cases we would have been seeing would have been substantially lower. Now, this allows us to make some conclusions. First conclusion is that lockdown decreases the amount of growth that we see. And it does survive a pretty significant amount, as seen under the lockdown efficacy table. So we're able to conclude that lockdown is shown to be effective while in place. We are also able to conclude from our dynamic model that due to the fact that it's able to, given 10 days data, predict 17 days out in advance, we're able to say that it is accurate and it is useful. So the longevity of this model combined with its inherent accuracy allows the future behavior virus of the COVID virus to be modeled successfully. So we're able to say the lockdown is shown to be effective while in place and the virus may be modeled successfully. So the goals of this project have been met and a greater understanding has been gained. Thank you.